Okay, hello everyone. Welcome. Oh, that's crackly, isn't it? Welcome to another Wednesday evening at the Institute of Astronomy. I'm here with Dr. Floor Van Leeuwen, who is going to tell us all about how stars get their colours and how stars work. As you've noticed, I think it's a cloudy evening, so there's going to be no stargazing, but we give you tea and biscuits instead, and then there's going to be a second talk from the Cambridge Astronomical Association, also talking about stars, so sort of a double bill of stars separated by tea and biscuits as a consolation for this cloudy evening. So yeah, thank you so much for coming. And yeah, I'm going to hand over to our headline speaker.
Yep, that should work.
Wonderful.
It's on. Right, good evening everyone. So we'll look a little bit through the stars today, and specifically the color. So to show you a little bit of an example here, we've got the Hyades on the left. And you see there on the very left, there's a very bright star that has nothing to do with the Hyades, that's Aldebaran. But within the cluster there, you see a number of red stars, same sort of brightness as the blue stars, and that's one of the things we'll come back to. And the Pleiades on the right, where we don't see any of these red stars, but we see plenty of blue stars there. So what's the meaning of those colors of the stars? Well, the interpretation of the colors is that it has to do with temperature of the stars. The early interpretation of the colors, people assigned letters to them. They classified them, so they gave them A, B, C, etc., etc. We still use those letters, except that they have been mixed up, because what they did originally wasn't quite right in terms of the sequence. So we now have a sequence which says O, B, A, F, G, K, and M. And you can recognize that in the early days there were a lot of male astronomers, because they thought that this would abbreviate to "Oh, be a fine girl, kiss me." I don't think that would be still acceptable these days. So color indicates temperature, and that is to do with what we call the black body radiation. What we observe here is only that bit in the spectrum there, but the light comes in a whole range of wavelengths. So when you have a hotter body, it radiates more at bluer wavelengths. When you have a cooler body, it radiates more at redder wavelengths. So the red stars are the cooler stars, and the blue stars are the hotter stars. When we look at the actual spectra that we take, so go back from here. So just look at that range between 300 and 1100. That's what you get in spectra. So the spectra, that little bit from the spectra that you see in the visual wavelength. So the very blue ones are the hottest stars that we observe. The very red ones are the coolest stars that we observe. Yeah, so you see the reflection there of the temperature in the spectra. So we know one thing, that is that the blue stars are very hot, the red stars are quite cool. So we observe stars at different distances. Yeah, the colors of the stars remain the same, except for some absorption of the blue light, which happens because of dust that you get between you and the stars. But we're not going to bother about that at the moment. To understand the processes that take place in the stars, we need to know their actual brightness. So because we observe only an apparent brightness, that depends on the distance at which we see the stars. So first we need to observation that can connect the apparent brightness with the colors. So that's the first thing we're going to look at. We can learn a lot from the movement of stars on the sky about stellar brightness. There are two fundamental types of movement. The first is the parallax, which is an apparent movement. I will come back to that later. And we have the proper motion, which is the actual projection of the movement of the star relative to the sun as projected on the sky. In the late 18th and early 19th century, they already were measuring the first proper motions of stars. And they saw some very high proper motions there. They expected, quite rightly, that nearby stars would show generally larger proper motions than faraway stars. Simply, if you have the same sort of motion but at different distances, it looks much more when it's nearby than when it's far away. So Friedrich Bessel used that in the early 19th century to identify the star 61 Cygni as a star that would be a good candidate to measure the parallax of. And that's the first star that anyone measured the parallax of in 1838. And it was actually done quite accurately. So let's look at how the stars move all. I hope I can get this to, yeah. So if you see the curly thing there, the curls are from the parallax, and the movement down is from the proper motion. And you see all the stars are moving around. This is much exaggerated from what's happening in real life. Yeah, in real life, these motions are all very, very much smaller. You want me to show it again? See if I can. Yeah. There are all kinds of things happening here. You see the very fast movers. There's going. Yeah, and it's measuring those movements over a time interval of years that can teach us both the proper motions and the parallaxes of the stars. So the proper motions at the end of the 19th century, they were available for quite a few stars already at that time. And that showed that there was a problem with the red stars. There appeared to be bright red stars with small proper motions and faint red stars with large proper motions, which seemed to be completely contradictory to what they were thinking of, namely that large proper motions would mean nearby and small proper motions would mean far away. And here the small proper motions were faint and the large proper motions were, and the large proper motions were faint and the small proper motions were bright. So what was going on there? Let's first see how it looks like. So we had on the left here, the big blob there on the left are the small proper motions, the very bright stars. So things get brighter to the left and fainter to the right. And the blob on the right there are the faint stars with the high proper motions. If you look at it on the sky, all of these stars on the sky, you see the same thing. Yeah? So every arrow shows the proper motion, and the faint stars are the dark blue ones, and they show the large proper motions. And the green ones and the red ones, they show generally very small proper motions. So let's take another step and look at the clusters. So we have star clusters. The very clear ones are the Hyades and the Pleiades. If we look at the Pleiades here, so there we have got the Pleiades on the right. On a clear night at this time of the year, you can see it very nicely. So there we've got a map of the bright stars of the Pleiades. If we put a lot of stars there down to about some faintness here, there are lots of stars there. Yeah. Now you add to that the motions of those stars. Yeah. It's a bit of a mess. Yeah. But there are things visible here. First of all, you see the arrows there pointing to the left. They point all towards the Hyades cluster. There are stars from the Hyades cluster which are in front of the Pleiades. And there's a whole bunch of stars that all go diagonally to the left down. And they're the stars of the Pleiades cluster. We can separate them. There we've got the stars from the Pleiades cluster. So they all move in the same direction. That's how you recognize the stars in the cluster. They all have the same, what we call proper motion. You separate them. So you see that they're all the same, and you see that they're also connected to those bright stars again. What does it mean? Well, it means that we have groups of stars on the sky with proper motions that are all the same. And for the proper motions to be the same, means that they are moving all in the same direction. They're moving together. Yeah, and as they're moving together, they're likely to be bound together, and have always been bound together. Now, if they're bound together, it means that they're all at the same sort of distance from us. Yeah? And if they're all at the same distance from us, it means that we can compare within that group, we can compare stars of different colors for their brightness. So we can see within the cluster how the different brightnesses relate to colors. And that's the first thing that people were doing around 1910, 1915. So we have different clusters with different prop motion. Let's take one step back and we compare the Hyades and the Pleiades clusters to see how clear this sort of whole picture is. So there we've got the Hyades cluster in prop motions. Now the Hyades cluster is very big compared to the distance from us. So it is relatively close by. And as a result of that, you get a projection effect. So when things are at large angles of the sky, they project differently at different points. So that's why you get this sort of picture of things moving all into one direction. That's the Hyades cluster. The Pleiades is right behind it, there. And if we zoom into that, you see the difference in the motions. Yeah, so the Pleiades all the gray arrows, and the Hyades all the red arrows. So that's how you distinguish the clusters from the field and from each other. They all have their own specific motions on the sky. So you can separate those groups. So, the relation between the color and the brightness for the stars. So the first relation to the color and the brightness within the cluster was established by Hans Rosenberg in Göttingen, based on the Pleiades again. And it was based on an idea that came up in a discussion between Hertzsprung and Schwarzschild in Göttingen around that time. Hertzsprung is on the left there, Schwarzschild on the right. Hertzsprung is then his name is associated with this relation, which is very often referred to as the Hertzsprung-Russell diagram. But I won't bother you with that too much. Hertzsprung was director at the Institute in Leiden, where I've been using plates that were developed by him and taken by him in the 1970s. So there we've got the first relation between color and brightness. From left to right, you go from blue to red, and from bottom to top, you go from faint to bright. These relations were obtained with photographic plates. So this is at the time that the first photographic plates that were sensitive at the visual were implemented. Before it was just photographic plates that were only sensitive in the blue, but now we got sensitive in the visual range, so in a redder band. And by comparing the brightness of stars on the plates that were taken, photographic plates that were taken in the redder band with those in the bluer band, you could get the differences and the relation between the difference between those stars that are in the cluster. So they already knew quite well which stars were in the cluster because of the prop motions. Yeah, and for the Pleiades cluster, the stars are very nicely separated from the field in prop motion. So all that worked nicely together for the Pleiades. For the other clusters, it became much more difficult. So we take modern observations and we look at the observed relations between color and brightness. So here we have two of them, for the Pleiades again and the Hyades. The Pleiades at the bottom and the Hyades at the top. So the difference here is because of the difference in distance. Yeah, the Pleiades is further away than the Hyades. So the Pleiades stars are all fainter at the same brightness, at the same color than in the Hyades. So if we really want to do something with it, we need the distances. Yeah, because without the distances, it's difficult to actually interpret this further. So, for the distances, the best method to measure distances accurately is a stellar parallax. That's the most direct way of measuring a stellar distance. What do we do there? Well, we do a bit of trigonometry there. a little bit of trigonometry. We use the baseline. We use as baseline, we use the orbit of the Earth around the Sun, which is a mere 300 million kilometers. And then we measure the difference in angle at which we observe a star during the time that the Earth moves around the Sun. As the Earth moves around the Sun, the star describes a tiny little ellipse on the sky. And the size of that ellipse tells you how far the star is away. That's the trigonometry. Now the problem is that those angles are extremely small. Yeah, so the largest angle that we have and the shortest distance is less than an arc second, is around 0.7 of an arc second. So it has been difficult to start measuring these things from the ground. We now measure these things from satellites, and I'll come back to that in a minute. But to get an idea of measuring the distances of things like these clusters that we were talking about, you need to get really, really very accurate data, which is difficult to get. So, for measuring parallaxes, that was done with ground-based observatories. Actually, before this, there was a little bit more with the heliometers that Bessel used and people after him, but after that it became very long focus refractor telescopes like the Yale telescope with photographic plates. They were taking photographic plates at different times of the year and comparing the positions as they developed over the years. The very long focus was needed to get a high magnification factor because you're trying to measure extremely small displacements. You're doing differential measurements. You're measuring relative to a sort of background of stars, which always gave a problem because also these background stars have got a parallax, and it's difficult to define exactly how much that is. You had limited access to the sky because you can't move your telescope from one part of from one part of the world to another part of the world, so you have only one hemisphere available to you. But it has been the main source of parallax measurements up to about the end of the 1980s. It's no longer relevant. Something has come in between, and that is the special design satellite missions. Double telescope on the satellite, full sky survey, single focal plane, both fields projecting on the same focal plane, and we get absolute measurements of the parallaxes because of this system. I won't bother you with the details, that's by itself a whole 20 minutes or so to explain. But the absolute measurements is important because it's no longer relative like we did from the ground. First mission was Hipparcos. I'll come back to it in a minute. And the current mission is Gaia. Both of them are European Space Agency missions. The European astronomy has taken a huge lead in all this work. Yeah, there's no other agency that does anything comparable. There are some differential measurements done with Hubble Space Telescope, but that's on a very small scale, and it's differential. So the Hipparcos satellite was launched on the 8th of August 1989, operated for 3.5 years, and used a predefined catalog of about 118,000 stars to observe. It was the first demonstration of space astrometry. Yeah. We have increased the available accurate parallaxes by a factor of 100 or more, and the accuracy of those parallaxes by at least a factor of 10 to 100. So the impact of that was enormous already at that time. It was first published in 1997, and then I did something about it and published the whole thing again in 2007. The Gaia mission is still running. It's again a project of the European Space Agency, launched about 9 years ago, in operation since 2014, and we had a third data release earlier this year in June. We're talking about extreme accuracy measurements of proper motions and parallaxes for around 2 billion stars, 2 times 10 to the 9 stars. Extreme accuracy, okay. We're measuring parallaxes at accuracies of about 10 microarc seconds. Now, to get an idea of what that means is, you try to measure here from the distance from here to London. Yeah, and use that trigonometry for that. So you need a baseline for that. So how big is the baseline? Baseline is no more than the thickness of a hair. Yeah, the relative, to get that sort of accuracy. So in comparison, the distance between the stars that we measure, the distance of, to the baseline of the Earth's orbit around the Sun, is like the distance from here to London and a baseline of the thickness of a hair. Yeah, so you really talk about extreme technology that's being used here, and that allows you to actually see quite far out around the galaxy, but still only within the galaxy, hardly anything beyond that, because space is big. So now we have got parallaxes, and we go back to the diagram that we showed earlier on the Pleiades and the Hyades. When we've got the parallax measured, we can calculate what the brightness of the star is at any sort of distance. Yeah, because we can correct for the brightness effect on the distance. So we normalize that to a distance of 10 parsec. That's a distance at which a parallax would be 1/10 of an arcsecond. That's just a standard that's been accepted widely. So we do that here for those two diagrams of the Pleiades and the Hyades, and then they fall nicely on top of each other. Yeah, so now stars of the same color have roughly the same brightness. There's still small differences there. On the left you see the difference, the lower part is the Pleiades, which is younger. You see the more massive stars, and for the Hyades it's older, and these stars have moved away already, and we'll come back to that in a minute. Also what you see there on the very bottom there are the white dwarfs in the Hyades cluster. We'll come back to that in a minute too. Back to our red stars that we started off with. So that is the diagram that we had. But now we have got parallaxes for these stars. So what can we tell about the parallaxes? Well, okay, we can assign brightness to these two blobs of stars. So we do that. And there we see that the blob on the left is all intrinsically very bright. The blob on the right is intrinsically faint. Yeah. Now we can, instead of using the apparent brightness, we can use the calibrated brightness at a 10 parsec. And then it looks that way. So now everything is back to the same 10 parsec distance in all the groups. But it's only the brightness that we've done this way. We can do the same with the prop motions. And then you see that they, in terms of the motions of these stars, they show very much the same motions. Whether we look at the bright stars that are the very big bright stars or the very small faint stars. They all have the same motion. And the only reason that we saw it differently was that the bright stars you can see much further away. So we can see them with very much smaller motions than the faint stars we can only see nearby. So now we take all of the stars, the whole sky, as observed by Hipparcos in this case, and we look at the relation between the color and the absolute brightness. Yeah, and we get a diagram like this here. And there, the big blob there on top are the red stars that we were looking at, the bright red stars. Now we come at explaining here. So the spectral types that we were talking about earlier on, the different types, they see here, you see them here in the diagram. The very left there at the top are the O and the B stars, and then you get the A stars, then the green is the F stars, and the yellow is the G stars, and then the orange is the K dwarfs, and then the red are the M dwarfs. Yeah, and then on top there are the G, K, and M giants. That's what we can do with Hipparcos. Note that the relations here are very much broader than what we've seen in the clusters. The clusters, they were all very narrow relations, but here they're much broader. The reason is that here you get a mixture of different ages, stars of different ages, different chemical composition, yeah, which have different evolution behind them. There we've got the red giants that we were talking about, and there we've got the red dwarfs. Now we go to Gaia, and it looks an awful lot more complex. So what we saw before here is only the top part of that diagram, with Hipparcos, but Gaia measures far fainter stars than Hipparcos did. So with Gaia, we see the entire diagram of all the different types of stars. And then we see, so Gaia measures about 20,000 times more stars than Hipparcos did, and measured accuracy 10 to 100 times better than what Hipparcos did, but using the technology that was initially developed for Hipparcos. So there we've got what we call the main sequence. The main sequence is the time that the stars spend most of the time on, and it's a time where they are, as they say, burning hydrogen. So that's the basic process of hydrogen fusion happening in the stars. When that's finished, the stars move to what we call the red clump. And in the red clump, they start burning helium. So while they were burning hydrogen, they collected more and more helium in the core. And at a certain point, there's not enough hydrogen anymore to keep the hydrogen burning running, and the star start to collapse in the core and expand in the outer parts, and then at some point the pressure in the core becomes good enough to start burning helium. That's what happens in the red clump. But it lasts only a very short while. And then it moves away from there, and then a whole lot of different things are happening depending on the chemical composition of the star and things like that. And that's what we call the giant branch. And then when all that is burnt out, it moves all the way down, and it becomes a degenerate body, which we call the white dwarf. The white dwarf is completely degenerated material, clumped together, a very tiny blob, and it's effectively a dead star. A dead star that's only still radiating because it's still very slowly contracting, and as a result of that radiating. So there we've got it. We started off with the colors of the stars and how they are related to temperatures. We looked at how the proper motions of the stars helped find the relation between the color and the brightness, identify the two types of red stars. We looked at the stars in the clusters, how they show details in the relation between color and brightness. We saw how the parallax measurements allowed to directly compare the clusters. And we showed that high accuracy parallaxes for large numbers of stars finally showed various aspects of stellar evolution as reflected in the color-brightness relations. There's a whole lot more that you can look at. These are a number of some of the links that can be used. For Hipparcos, we've got basic information. We've got an interactive data access program. And for Gaia, we've got a UK site that gives a lot of up-to-date information too. So thank you very much.
Wonderful. So before we have a break, do you have any questions for Floor?
This doesn't sound good, does it?
I don't believe there's not one question.
You had a graph that had something like movement over 15,000 years.
18,000, yeah, there's something like that.
So how does that happen? I mean, you haven't had astronomers around that.
No. So what you have is you have a movement per year, and you extrapolate it to 18,000 years, just like that. You can do that simply because the 18,000 years is a very short time scale for stellar interactions. Yeah, you can't do it over things like several 100,000 years. Then things go wrong. Yeah, then you get all kind of interaction and other things that you have to take into account. But 18,000 years is a very short time scale. Yeah, so you can see how things develop over that sort of time scale. But 18,000 years is relevant for human history. Yeah.
There's a question over here at the front.
So the spectrum of colors of the stars, I mean, we see sometimes some blue, red.
Sorry?
Can we see all the colors, like green?
You can see stars in all the colors. Let's say it that way.
The naked eye?
Yeah. Well, you can see a few of those that are bright enough. The problem is your eye is the color detector in your eye is not as sensitive as the black and white detector in your eye. Yeah, so you will see most of it just black and white, but only the brightest stars you see the color. So Aldebaran, you see the redness of it. Betelgeuse, you see the redness of it. Yeah, Sirius, you see the blueness of it. Yeah, but for anything that is fainter, it's a lot more difficult. Once you put your binoculars to it, you can see already a lot more in colors. Yeah, you can see in the Hyades, you can see those red giants in there. Yeah, but it really comes to life when you start taking the photographs, and because that doesn't have that sort of limitation. It's all there, but yeah, it's not so easy visible always. Yeah.
Wonderful. Anyone with the last question before we go and have a tea break? Yeah, go on.
In the very beginning, you show us some animation about the movement of the stars. So may I know that the movement is talking about movement in several minutes, several days, or actually?
It's several years.
Several years.
Yeah. It's every year that it makes a full loop. Yeah. So it effectively showed over about 3.5 years. So it was Hipparcos data, I think, because the mission lasted 3.5 years, but blown up. So everything was made a lot bigger than it actually was on the sky.
Great, wonderful. Okay, so let's go for a tea break. As a favour to me, if you could take your handouts and sort of put them in the recycling bin rather than leaving them, save me the job of collecting them all at the end. So yeah, let's have tea and biscuits. Before that, let's thank Floor. Awesome, thank you.
Yeah.
You're probably going to get inundated with questions now. Do you want a cup of tea or something?
Yeah, but I don't want to stay long at all.